Hey everyone, welcome back. I am so incredibly excited to have you here for the 7th explainer in our complete waves course. Today, we're taking on a massively important, absolutely crucial topic for your IGCSE 0625 Physics syllabus. We are talking about sound waves. Now, if you've been following along with our earlier explainers on general wave properties, you are actually in a fantastic spot because so many of those foundational rules apply perfectly to what we're doing today. We're going to break down exactly what sound is, how it behaves, and, most importantly, how to completely hack those specific past paper questions examiners love to throw at you. So grab your notes, get focused, and let's conquer the sound section together.
Okay, let's dive into our checklist for today. First, we'll cover the nature of sound waves. Then, we'll hit pitch, loudness, and hearing. After that, we've got the speed of sound explained, followed by reflection and echoes, and finally, we'll wrap up with ultrasound and its practical uses.
All right, kicking things off with Section 1, the nature of sound waves. Let's look at the absolute core characteristics of sound. First and foremost, sound is a mechanical wave, which means it requires a vibrating source. Think of plucking a guitar string or even just feeling your own vocal cords when you speak. Without a vibrating source, sound literally cannot exist. Now, unlike the transverse waves we looked at earlier in the course, the ones that move up and down, sound propagates as a longitudinal wave. This means the particles of the medium vibrate parallel to the direction the wave is actually traveling. They just move back and forth along the exact same path as the wave itself. And because sound travels by particles physically bumping into their neighbors to pass the energy along, like a line of dominoes, having a physical medium, whether that's a solid, a liquid, or a gas, is absolutely necessary.
So, as those particles vibrate back and forth, they create a very specific pattern. On one hand, we get what are called compressions. These are the high-pressure regions where the molecules get pushed tightly together. On the flip side, we have rarefactions. These are the low-pressure regions where the particles are spread further apart. It's like a giant invisible accordion playing in the air. And here's a quick pro tip. If you increase the amplitude, basically if you make the sound louder, those compressions get squeezed even tighter and the rarefactions become even more stretched out.
Let's trigger our Learn, Apply, Score loop right now. Here's a classic previous year IGCSE question that examiners love using to test your understanding of wave mediums. State why sound cannot be heard in space. Think about what we literally just talked about regarding particles passing energy to one another. Got your answer?
Here is the exact examiner-approved answer you need to write down for full marks. Space is a vacuum and lacks a medium for sound waves to travel. It really is that straightforward. Because there are no particles floating around in a vacuum to vibrate and transmit those compressions and rarefactions, the mechanical energy has nowhere to go. Simply put, no medium, no sound.
Moving right along to Section 2, pitch, loudness, and hearing.
The human ear is a genuinely amazing organ, but, it does have its limits. Our audible range sits between roughly 20 Hz and 20,000 Hz. But how do the actual physical properties of a wave translate into what you and I hear? Well, the maximum displacement of the particles, which is the amplitude, determines loudness. Larger amplitude, louder sound. Meanwhile, the number of vibrations per second, which is the frequency, determines the pitch. So a higher frequency, meaning way more vibrations happening every second, gives you a higher pitch, kind of like a sharp whistle. Oh, and anything below 20 Hz, we call that infrasound. Anything above 20,000 Hz, that's ultrasound.
Okay, time for another rapid-fire past paper question. This one is incredibly common and it directly tests the relationship between wave properties and human perception. The question is, state the quantities that determine I, loudness, and II, pitch of a sound wave. You just need to match the human perception to the correct physical property.
And the answer is, loudness is determined by amplitude and pitch is determined by frequency. So the crucial takeaway here is that you must never, ever mix these two up on exam day. Remember, amplitude is volume, frequency is pitch. Lock that vital pairing into your brain right now.
Jumping into Section 3, the speed of sound explained.
Sound speeds aren't fixed. They actually vary dramatically depending on the state of matter they're traveling through. In air, a gas, sound travels at roughly 330 to 340 meters per second. But drop that exact same sound into water, a liquid, and it rockets up to around 1,500 meters per second. Move it into a solid, like a block of steel, and it blasts through at an unbelievable 5,000 meters per second. Why does it do this? Well, it's all about how tight the particles are packed. The stronger they're bonded, the faster they can bump into each other and pass that vibrational energy along. Solids are packed super tight, gases are all spread out.
So how do we actually measure this speed in the real world? For your syllabus, you need to know two main practical methods, the clap stopwatch method and the flare gun method. They both follow the same simple steps. First, you stand a known large distance apart from a friend. Second, your friend creates a visual cue along with a really loud sound, like clapping huge blocks together or firing a flare gun. Third, you start your stopwatch the exact fraction of a second you see the clap or the flash, and you stop at the moment you hear the bang. Finally, you calculate the speed by dividing distance by time. The absolute genius of using a visual cue here is that light travels incredibly fast, almost instantaneously over these distances. Using light as your starting pistol entirely eliminates human reaction time errors from the very start of your timing.
All right, on to Section 4, reflection and echoes. Just like light waves bouncing off a mirror, sound waves can reflect too. When sound hits a hard, flat surface, it bounces back following the exact same rule you already know. The angle of incidence equals the angle of reflection. When this reflected sound comes back and is heard as a distinct separate event from the original noise, we call that an echo. But, and here's a really crucial detail for your exams, for our human brains to actually process it as a distinct echo, there has to be a time delay of at least 0.1 seconds between the original sound and the reflection.
Let's see how directly that syllabus definition translates into a standard past paper question. The question simply asks, define an echo. While it might seem a bit too simple, be careful. The examiner is looking for very specific keywords here to award you full marks. To guarantee you get all the marks, here is your perfect answer. An echo is a sound heard after reflection from a hard surface, occurring when there's a time delay of at least 0.1 seconds. By explicitly mentioning both the reflection off a hard surface and that specific 0.1 second time delay, you show the examiner you completely grasp the physical requirements for an echo to actually exist.
Finally, Section 5, ultrasound and practical uses. Let's get into the high-value exam stuff. As we established a few minutes ago, ultrasound is any sound wave with a frequency greater than 20,000 hertz, so it's totally inaudible to humans. But why is it such a massive deal in physics and engineering? Well, it's all about boundaries. Ultrasound waves uniquely reflect whenever they hit a boundary between materials of different densities, a sudden change in what we call acoustic impedance. This allows us to use it for non-destructive testing. Think about trying to find a microscopic hidden crack inside a thick metal pipe. The wave bounces back early from the tiny air gap inside the crack, revealing the flaw without breaking the pipe. It's also heavily used in medical scanning to map soft tissue or for prenatal baby scans because it's non-ionizing, meaning it's so much safer than X-rays. Oh, and it's the core technology behind sonar, allowing ships to map deep seabeds or track submarines.
Now I need you to focus very, very closely on this next concept. The formula is distance equals speed multiplied by time, all divided by 2. This right here is the absolute biggest trap in the entire sound syllabus. When a ship sends a sonar pulse down to the seabed, the time you record is the time for the wave to travel all the way down, hit the bottom, and travel all the way back up to the ship. It is a round trip. If you just blindly multiply speed by time, you are going to calculate double the actual depth. You absolutely must remember to divide your final answer by 2.
Let's put that exact trap to the test with a high-stakes, past-paper sonar calculation. A ship sends an ultrasound pulse. It takes 2.5 seconds for the echo to return. The speed of sound in water is 1,500 meters per second. Calculate the sea depth. I want you to mentally apply the formula and the trap we literally just discussed before I reveal the steps. Give it a shot.
Okay, let's methodically break down the math. Step 1. Calculate the total distance the sound wave travels by multiplying the speed, which is 1,500 meters per second, by the total time, 2.5 seconds. That gives us 3,750 meters. Step 2. Because that 2.5 seconds represents the echo traveling down to the bottom and back up again, we have to divide 3,750 by 2. Step 3. Our final, guaranteed full mark answer for the actual depth of the sea is 1,875 meters. Make sure you show your working out clearly, just like this on your exam.
All right, what a session. We've covered the mechanical nature of longitudinal sound waves, how amplitude and frequency shape volume and pitch, the varying speeds of sound through different mediums, and the incredible density-revealing power of ultrasound. But let me leave you with this to ponder before we go. If ultrasound fundamentally relies on reflecting at boundaries of different densities without causing a single scratch of damage, how else could engineers utilize this invisible wave in the future? From microscopic medical robotics to exploring completely alien oceans in deep space, the applications are literally endless. Keep questioning, keep practicing those past paper questions, and I will see you in the next explainer as we continue our awesome journey through physics.